Hello everyone, I am Amit K. Jain, working as Assistant Professor in STM Institute of Technology, Ujire. Welcome to today's control system session in relation to Module 5, State Variable Analysis. Again, the topic for today's session is State Model. So now, the problem statement is represent the transfer function given below in a state model, and this is form 2. Form 2 is we will have a polynomial in the numerator. In the previous video, we have seen form 1, that is if we have a constant in the numerator. But here we do not have a constant in the numerator, we have a polynomial in the numerator. Again, to know what is a state variable, what is a state model, how to develop a state model for a given differential equation, how to develop a state model for a transfer function. If there is a constant in the numerator, that is form 1, you can go through the previous 3 videos. So this is the 4th video in a series of videos in relation to state variable analysis. So now again, here the first step is represent the given transfer function in the form of block diagram. Again, we will arrive at this block diagram. Again, you can observe here u of s is the input, y of s is the output, and this is your transfer function. We know, right? Transfer function is the Laplace transform of output to the Laplace transform of input, assuming that initial condition is 0. So this is our output and input, and this is our transfer function. Now you represent the above block diagram as a cascade of 2 blocks, that is you separate numerator from the denominator now. That is u of s and intermediate signal c of s and output y of s. Here if you observe, what we have done is we have written denominator as separate and numerator as separate. In the given transfer function here, which is the denominator 1 divided by s cube plus 9s square plus 26s plus 24 is written as the first block, then that is multiplied with only the numerator part, that is s square plus 7s plus 2. So now we have written the given transfer function in form of a block diagram, and then later we have represented that in the form of 2 series connected blocks. So the same block diagram is represented here. So now here what we will be doing is, for the first block we will find state equation, and for the second block we will find output equation. So here the output of the first block is, we know that output is nothing but input multiplied by transfer function, right? So output is c of s will be equal to input u of s multiplied by transfer function. You will get u of s divided by s cube plus 9s square plus 26s plus 24. Again you perform cross multiplication, you will get u of s into 1, that is u of s. If you multiply c of s with this term, you will get an expression like this. Now again you apply inverse Laplace transform, we will get an expression like this. Again we have already discussed all these steps in the last video, so in detail I will not be explaining. If you want a detailed explanation, you can browse through the previous videos. Now this is the differential equation which we have arrived at for the given transfer function. Now you already know, if you have a differential equation, how to develop a state model. So we will follow the same procedure. So here we have c triple dot of t, so the highest order is 3, so we will have 3 state variables. So those state variables are c of t, c dot of t, and c double dot of t. x1 of t is c of t, x2 of t is c dot of t, and x3 of t is c double dot of t. Now in order to find state equation, we need to find x1 dot of t, x2 dot of t, and x3 dot of t. So I will quickly go through this. So these are all the things which we have already discussed in the previous video. So now we will find x1 dot of t. Again these are the already established state variables. Again we know that x1 of t is c of t. Differentiate that particular expression, we will get x1 dot of t is differentiation of c of t with respect to t is c dot of t. So c dot of t is nothing but x2 of t, so we will get x1 dot of t is x2 of t. That is refer equation B. Similarly, what is x2 of t? That is our second state variable, which is c dot of t. Again differentiate x2 of t, you will get x2 of t is equal to differentiation of c dot is c double dot. But what is c double dot? x3. So you will have x2 dot of t is x3 of t, which is our second state equation. Now for C triple dot of t, we know that x3 of t is C double dot of t. Differentiate x3 of t, you will get x3 of t is C triple dot of t. Again, we do not have any relationship which relates C triple dot with a state variable or input. So now we will achieve that. So we will find C triple dot of t, and we already have a differential equation in this form. Again, we need C triple dot of t, right? So rearrange this expression for C triple dot of t. You will get an expression like this. Now here you need to represent this particular expression in form of state variable and input. Again, you observe what is C triple dot of t, x3 dot of t. What is C double dot of t, x3 of t. What is C dot of t, x2 of t, and what is C of t, x1 of t. You just substitute. So now here, if you can observe, we have an expression for x3 dot of t, that is state equation, represented in the form of only state variables and input. So now if I rearrange this, I will get x3 dot of t is equal to minus 24 into x1 of t, minus 26 into x2 of t, minus 9 into x3 of t, plus u of t. Now represent all three state equations in form of state model. So you will get x dot of t is equal to a into x of t. Again, x of t is x1, x2, x3, plus b, again the b matrix, into u of t. So regarding how we have written a, how we have written b, we have already discussed in the previous two videos. So please refer previous videos to know how to write a and how to write b. Now we will develop output equation. So now output equation is y of t is equal to c into x of t plus d into u of t. So now again we will refer the block diagram which we had written earlier. Now here you see y of s, if we want y of t, it will be derived from y of s, right? So what is y of s? The output of the second block. So what is y of s here? Again, y of s is c of s multiplied by s square plus 7s plus 2. So you will get an expression like this. Apply inverse Laplace transform. So you will get y of t as here c double dot of t. S into c of s will become c dot of t. 7 is written as it is. 2 into c of t. So now represent this in the form of standard output equation. But before that, this is not yet in the form of state variable, right? So represent this in the form of state variable. Y of t is c double dot of t is x3 of t, c dot of t is x2 of t, and c of t is x1 of t. See, these are our state variables. So now we have our output equation like this, just rearrangement. Now represent that in the form of standard output equation. So representing equation 4 in the form of standard output equation, we will get y of t is equal to c into x of t, again this is x of t, plus d into u of t, but here d into u of t will be 0 since there is no input term. But in case you are wondering how we have written c is associated with x of t. So x1, x2, x3, the coefficient of x1, x2, x3 in y of t is nothing but c. You can observe here, in y of t, the coefficient of x1 is 2. So we have written 2. The coefficient of x2 is 7. So we have written 7. The coefficient of x3 is 1. So we have written 1 in relation to x1, x2 and x3. Now if you write both the equations, then the combination of both the equations, that is state equation and output equation, is called as state model. Again, you can observe state model represented in the general in its general form, x dot of t is equal to a into x of t plus b into u of t. Similarly, output equation represented in its general form, y of t is equal to c into x of t. Here d into u of t is 0. Again, this is how we will develop a state model for a given transfer function if it is in form 2, that is if there is a polynomial in the numerator. If you have any doubt in relation to this problem or similar kind of problems, feel free to contact me. Once again, thank you for your time.